So far, in our discussion on eigenvalues and eigenvectors, all of our characteristic polynomials have factored completely over the real numbers. This, however, is not always the case. For example, the matrix A with columns 0, 1 and minus 1, 0 has characteristic polynomial lambda squared plus 1, which has two complex roots, I and its complex conjugate minus I. So in order to understand the situation where a matrix has complex eigenvalues, we need a little refresher and a new perspective on the complex numbers. First of all, recall that complex numbers are those numbers z, which can be written as a plus b times I, where a and b are both real numbers. So we can perform arithmetic with complex numbers. For example, the component-wise sum and difference of two complex numbers is, again, a complex number. We can also scale in each component a complex number by a real number, s. And of course, this should sound pretty familiar. If we take two vectors, z with entries ab and w with entries cd, then of course we can add these two-dimensional vectors together by adding the components, and we can scale one of these vectors by a real number s. So if we were to discuss abstract vector spaces, a set such as C that is equipped with the operations of addition and subtraction, an additive identity such as the zero vector or the zero complex number, and scalar multiplication by R is called a real vector space. In this particular case, we can actually identify the complex numbers with the set R2, which makes C a two-dimensional real vector space. But of course, we know that more is true. We can also multiply any two complex numbers together and get another complex number. This action of the complex numbers on itself by multiplication endows the set of complex numbers with the structure of a one-dimensional complex vector space, analogous to the way we can regard the real numbers as a one-dimensional real vector space. So for our purposes in this class, our identification of the complex numbers with the two-dimensional vector space R2 will allow us to effectively reduce the case of studying complex vector spaces to the study of even-dimensional real vector spaces. However, this extra multiplicative structure on the set of complex numbers does raise one important question. If we identify complex numbers with two-dimensional vectors, and we have not defined the product of two vectors, then how do we interpret the product of two complex numbers? So reconciling this oddity between these two sets relies on analyzing our original matrix A. So if we think about a complex number, a plus bi, as a vector with entries a and b in R2, if we multiply a by z on the right, then we can see that we'll get the vector 0a minus b, 1a plus 0b, and this is the vector minus ba. If we rewrite this vector as the complex number to which is associated, we would have the complex number negative b plus I times a. And of course, if we think about negative 1 as being I squared, then we can rewrite this as I squared b plus ia. Factoring in I on the left, we're left with I times a plus ib. So this tells us that we can think of the matrix A as encoding, under this identification, multiplication by the complex number I. That is to say, if we draw ourselves a little diagram, we'll put complex numbers on the left, and we'll put their representation as two-dimensional vectors on the right. Well, we can think about defining a function which takes in a complex number and outputs the complex number I times that complex number. Similarly, we can define a matrix transformation using A, which goes from R2 to R2. It takes in a vector and outputs A times that vector. Now, of course, we have a way to move from the complex numbers to the real numbers by simply associating A plus IB with AB, and backwards by associating AB with A plus IB. And as we just saw, this association respects these two mappings, namely I times A plus IB and A times AB under this mapping are associated. So this is how we think about the matrix A as encoding multiplication by the complex number I. Now, if you recall, it just so happens that I was one of the two eigenvalues of our matrix A. It turns out that this is no coincidence whatsoever. In fact, for any complex number that we like, A plus BI, we can define a matrix A, B, minus BA, and that matrix, when it acts on the representation of another complex number, CD, will give us the representation of the complex number A plus BI times C plus DI. So in the next video, we'll see that if our matrix A has A plus BI and A minus BI as eigenvalues, then A will be similar to a matrix of this form.